Okay, so we will begin with questions for preparation for midterm. So the first question is equations for real, imaginary, and complex signal. So real signal equation, imaginary signal equation, and also complex signal equation. So if we have a signal xt that is a, e, j, 3 pi t, it is the complex signal, so it can be transformed using Euler's equation to real signal and imaginary signal. So a cos 3 pi t plus ja sine 3 pi t, and this is the real part of the signal, this is imaginary part of the signal, and altogether this signal is called complex, so having real and imaginary parts. So in the test you will have to select if it's real, if it's imaginary, or if it's both, that is complex. So this was the first question. Now let's go to the second question. So the second question is properties of continuous time and discrete time signals. So the first property is periodicity. So if we have continuous time signal, that the signal is xt a cos omega t plus phi 0, so then this signal is periodic if we have the rule that is correct. So is xt0, and there is xt0 plus period t, and if the value of xt is the same after adding period capital T to t0, then we can say that the signal is periodic. So this is in continuous time world. Now if we have discrete time, so we have n instead of t, and we have a cos omega n plus phi 0, and the periodicity property is the same, xn, x and 0 plus capital N. So here the basics is the same, however this signal is periodic only when f0, that f0 we can obtain from, if we turn this omega 0 to 2 pi f0. So then f0 should be k divided by capital N. We can add 0 also here. K divided by capital N. So N should be integer and K should be integer. So this means that discrete time signal is periodic only if its frequency is a rational number. Rational, it means that it is the ratio of two integers. So we cannot have period capital N to be 1.5 or 1.6, because if you remember, when we have a signal, we have here only 0, 1, 2, 3, 4, 5, 6. We don't have numbers with dots. So this is wrong for discrete time signals. The next property, as we could follow the book, it is that property number 2, it is that discrete time sinusoids whose frequencies are separated by 2 pi are identical. So as you remember, we said that discrete time signal is unique only if it has the frequency omega that is between minus pi and plus pi. So omega 0 should be between minus pi and plus pi. So if we write in frequency f, it should be minus 1/2 plus 1/2. So if we have omega k, that is omega 0 plus 2k pi, where k is equal to plus minus 1, plus minus 2, plus minus 3, and these signals having the frequency omega k will be identical to omega 0. So let's say we have omega 0 that is pi divided by 6. So omega 1 will be what? Will be pi divided by 6 plus 2 pi, it will be 13 divided by 6 pi. Omega 2 will be pi divided by 6 plus 4 pi. So it will be 25 divided by 6 pi. And this is identical to this and is identical to this. And another example, if we have omega 0 is pi divided by 7, we have omega 1 that will be pi divided by 7 plus 2 pi, so it will be 15 divided by 7 pi, and omega 2 will be pi divided by 7 plus 4 pi, so it will be 29 divided by 7 pi. So again, these all are identical. So these are identical in between, and these are all identical, all three, these three and these three, but these are unique and these are unique. Also these are unique. So the third property, so this was the example of aliasing. So the aliasing basically is that this frequency, signal having this frequency, is similar to this and is similar to this, but this signal is unique to this. Aliasing is having the same signals, although their frequency is separated by 2 pi. So these signals are called aliases, and this is the example of aliasing. If you get this, you will know. Now the third property is considering the maximum frequency. Basically, coming back to again this property in continuous time, if the signals are having different frequencies, they will be different in continuous time. So this holds only for discrete time. Third property is that considering the maximum frequency. So maximum frequency, as you can see from these, maximum frequency should be in discrete time world. It is what it is. F max we can write. It is 1 divided by 2, or if it is omega max, it will be pi. So it can be plus minus. So it will be plus minus plus minus. Maximum refers to plus sign, but if it's frequency, you know it is the amount of wiggling of the signal. So we can consider that also minus holds here. So in discrete time, maximum frequency, it is a half. Why? Because as I have showed you before in the lecture, we get one up, one down, one up, one down, one sample again up, one sample down, one sample up, one sample down. This is n and this is xn. So we see that here n is 2, k is 1 cycle, and therefore we have fk divided by n k divided by n, it is 1 divided by 2. Yeah, and we get a half. So this is considering the maximum frequency. In continuous time, maximum frequency is infinite. If we have continuous time situation, f max is infinite. Remember this. F max is infinite in continuous time. In discrete time it is different. Okay, so now we move to the next question. This was a bit longer question, and we can continue with the question that it is signal sampling and quantization. Number 3, signal sampling and quantization. So what is signal sampling? Signal sampling is when we have continuous time signal, some kind of continuous time signal where we have here t and this is xt. So we take evenly spaced, we take the values of xt, take the values of xt at equally spaced intervals t to obtain xn. This is continuous time signal and this is discrete time signal because it is sampling. Sampling can be called basically discretization, or it can be called in more detail discretization of x-axis or time axis. Okay, so taking the values of xt at equally spaced intervals t to obtain xn. So how it looks like? It looks like you have here, take this value at t. Now you're taking this value at 2t, taking this value at 3t, taking this value at 4t, taking this value at 5t, and so on. What's next? Next is that this capital T is called, let's write it S subscript. This TS is sampling period. Sampling period, it is the inverse to sampling frequency. Basically, detailed information you can find in the book that we have taught in the lectures. This is just short review here. And what's next? Next is that we have quantization. This thing called quantization is the discretization of y-axis or discretization of amplitude. Synonyms. Basically, if we say discretization, we refer, if we say one word discretization, we refer to sampling, to discretization of x-axis. So discretization of y-axis. So after performing this operation, we produced the signal. This is n, this is xn, but these signals have values. Let's say this has 4.6. Let's say this has 4.1. This has 3.8, and this has, let's say, 3.7. So after quantization, we get a signal that looks like what? So this signal basically is gets the value 5. So you can write that it is quantized signal, Q. So this gets the value 5, so it increases. 4.1 gets the value what? Gets the value 4. 3.8 gets the value 4. And 3.7 gets the value also 4. So they are increased. So all of these in this example, they get increased. You can find better example in the book in the end. Here is just short remembering of what we have learned. Now, fourth question: what signal can be called digital? Digital signal. Digital signal is both discrete in time and in amplitude. It has to be both. Discrete in time and in amplitude, both. Yes, both discrete in time and in amplitude. So sampled and quantized. And prefers to be also coded and coded. So it is digital. Discrete in time and amplitude, and coded, or in synonym, sampled and quantized and coded. So sampled and quantized is sufficient for the signal to be called digital. Coded is, we usually assume that it's coded. Okay, so we have finished with 4 questions. Now we have fifth question. So fifth question, it is I have to go back to the start. Fifth question is right here. It is discrete time signal equation. Discrete time signal equation. Continuous time signal equation. Conception of time. So let's begin with maybe the continuous time signal. So CT, it is xt a cos omega t plus phi 0. So basically we have here it is the amplitude, here it is the angular frequency, here it is time, here it is initial phase. omega is 2 pi f. In the book, if you read the book, in the book there is, for continuous time signals, there it is capital omega, so we can correct here. Capital omega, it's the same equivalent because they want to separate between them. Capital omega, and this small f turns to f capital. This is just to separate them theoretically in the book. It's just like agreement. So this is continuous time signal, and the concept of time is that time is from minus infinity to plus infinity. It has it can get any possible value. So 1.5, 1.6 values are allowed here. So in discrete time we have equation xn. It is a cos here small omega n plus initial phase, and here we have also respectively to that this equation we have the same equation 2 pi small f, and here we have n instead of t, and now n can obtain only values like 0, 1, plus minus 1, plus minus 2, plus minus 3, etc. And the values like 1.5, 1.6, they are not allowed here. Okay, in discrete time. Discrete time. No 1.6, no 1.5. So that's why n is integer. Yeah. Let's move to the next question. What is the relation of signal frequency to period? It's a very simple question. Most of you will know this. What is the relation of signal frequency to period? So if we have the relation is basically f, it is 1 divided by t, where it is frequency, it is period. So all of you know this equation. So if what happens if t increases, so what happens? We are dividing by a higher number, then f is reduced. Yeah, if t increases, then f is reduced, and the opposite also holds. Yeah, so be aware of this question. So question number 7. This is an exercise xn. We have a signal xn, discrete time signal, cos 4 pi divided by 5. So okay, so this we need to determine the period. What is the period? N. What is n? Here what we should know is that basic equation is xn cos omega n. So everything that stands in front of n is omega. So everything here that is in front of n is omega. So we can write that omega is 4 pi over 5. So then we can write that 2 pi f is 4 pi divided by 5. We can divide both sides by pi, and we find, and also we can divide both sides by 2. So we get what? We get 4 divided by 10. We divide by 2. It is 2 divided by 5. So n is 5, k is 2. So this signal is periodic, has the period of 5. Now, 8th question. 8th question is what we have already discussed. It might be confusing, so we may repeat it. So, question number 8. Unique and allies discrete time signals. Okay, their frequencies, not their frequencies. Their frequencies. What we have already discussed, it is that unique in discrete time, unique signals are the signals who have the frequency omega 0 that is between pi and minus pi, and because omega is 2 pi f, so if omega is pi, so then 2 pi f divide by pi, then we get what? 1 2 f, and f is what? Is a half. So it means that f here is a half. So this f goes here, it is here minus half f0, and it is here. That's how this came from this. So this is just derivation. What I want you to know here, and what is basically important, that unique signals, we can write this again. I just need to follow the paper. So unique signals from minus pi to omega 0 to pi minus half f0 to half. These signals are unique, having these frequencies. Now, if we take omega 0 plus 2k pi, where k is 1, 2, 3, etc., then we obtain aliasing, and these signals are allies to this omega 0. So we have unique, this is basically the example that I showed, that I previously couldn't draw probably very nicely, but here we get pi divided by 6, pi divided by 7. These signals are unique It means they are different. Yeah? Now, the signal that when we obtain by adding 2 pi, so plus 2 pi, we obtain 13 divided by 6 pi. Oh. And these are identical. Aliases. Here we have pi divided by 7 plus 2 pi. It is 15 divided by 7 pi, and these are also identical. Aliases. But these two, they are what? They are also unique. Yeah, because they come from different initial signals. Yeah, they are unique, they are different. But basically you need to know that pi divided by 6, pi divided by 7, pi divided by 8, anything that is between minus pi and pi, they are unique. Aliases is when you add 2 pi and you obtain aliasing. In order to go out of the aliasing, you take what? You do what? You take this, you subtract 2 pi and you obtain, so this is omega 0, and you obtain the unique or initial signal to be pi divided by 7. Yeah, you just subtract, because here it was added, here you just subtract. This should be clear because we repeated it once again. Now I'll just drop this away. Now we go to number 9. Number 9 is what? I need to check. Number 9 is maximum signal frequency. Maximum frequency in discrete time. Maximum omega, maximum f in discrete time. So we, oh sorry, I lost. So we already discussed that maximum omega is in discrete time is what? Is pi, and maximum f is a half. Why it is a half? We can write it plus minus also, because it is one sample goes up to its maximum amplitude, one decreases down to its minimal amplitude, one goes to the maximum, one to minimum, maximum, minimum. So this is maximal amplitude, this is minimal amplitude. Yeah, so this is xn, this is n. Should be clear. Yeah, that this is 2, 3, 4, 5. To determine the period, we in discrete time, this is what you need to remember, what we will repeat. We count the space as one space, two spaces. So here 2 spaces and 1 cycle from maximum to minimum to maximum. Yeah, 1 cycle. So we have k is 1, so f is 1 divided by 2. So f is a half, so omega will be 2 pi f. So 2 pi times a half, and it is pi. Yeah, so because these cancel each other. Okay, now let's go to 10. 10, okay, 10. What is 10? Sampling. Okay, sampling. Sampling of continuous time signals. Okay, x1 is x1t is cos 2 pi 30t. It's also written in this form, 2 pi f, in this form, so it would be easier to calculate. Yeah. Another one is x2t cos 2 pi 80t. What should be the sampling frequency or sampling rate in order to discriminate these continuous time signals in discrete time? So here we need to know the sampling theorem or sampling relation. So basically the equation that I want you to know is that f is capital F divided by Fs. So here it is, this is continuous time, frequency of continuous time signal. Continuous time signal frequency, continuous time signal frequency. This is sampling rate or sampling frequency. This is discrete time signal frequency here. So in order to, so from this you can derive very simply the sampling theorem using these assumptions we done before. So how? Because here we have discrete time signal frequency, and this discrete time signal frequency is equal to maximum, is equal to 1/2. So if we write here, substitute this f by 1/2, we get what? We get Fs is equal to 2f. So in order to discriminate signal, continuous time signal, CT signal, yeah, CT signal, whose frequency is capital F, we have to sample at sampling rate which is equal to 2f. So sampling rate has to be equal to 2f. So we had here, let's come back a bit up, we had 30, this frequency was F1 was 30, F2 was 80. So this was the formula, Fs is 2f, because sometimes it's written when we choose from lower frequency and higher frequency according to the maximum frequency. So it's written F max because it refers that we have to have in mind higher frequency. In this case it is 80. So sampling frequency should be Fs 2 times 80, and it should be 160 Hertz. That's the answer. Good. 11. Let's go to 11. It's again with sampling. just correct my paper. Good. 11. Signal xt. Signal xt cos 10 pi t. 10 pi t. Sampling rate is 80 Hertz. 80 Hertz. So question is, what is xn after sampling? We can find it easily. Xt, it is what? Cos 2 pi 5 t. According to this equation, f divided by fs, we can write that small f is 5 divided by 80, and we can get that it's 1 divided by 16. Now xn is what? Is cos 2 pi 1/16 n. Now it is equal to cos 2, it's not 2, cos pi divided by 8n. This is. So this is the discrete time signal we obtain. 12 is sampling theorem. Okay, sampling theorem is what we talked just before, like here. Here it is sampling theorem. Fs is equal to 2f. Okay, we can write that Fs is equal to 2f. So this sampling rate is called Nyquist rate, or Nyquist, I'll write in capital, Nyquist frequency. Nyquist rate or Nyquist frequency. So as you remember from the lectures, I said because when we're dealing with cosines, we can write this to be equal. When we're dealing with sines, we need this to be higher. So generally, the sampling theorem is written to be Fs is higher than 2f, or if we are comparing some frequencies, have lower and a higher, we write like this: Fs is higher than 2f max. Question number 13. Oh, it is more. We have a lot here to write. I will take new sheet. Question number 13. Okay, question number 13. Sampling rate we have 10 kilohertz. Xn we have 5 cos 2 pi a half n plus 6 sine 2 pi 1 divided by 4 n. So here we have make the inverse procedure. We need to find xt. So here again we have this equation. This is dt, this is ct. frequencies, yeah? So capital F is small f times Fs. And we now need to multiply. So we write that xt is 5 cos 2 pi a half times 10 kilohertz means 10,000 hertz. This will be now t plus 6 sine 2 pi 1 divided by 4 times 10,000. This will be t. Here it is 5 cos 2 pi 5,000 t plus 6 sine 2 pi times 2,500 t. And here we get 5 cos 10,000 pi t plus 6 sine 5,000 pi t. Probably correct. Okay, now we go to the number 14. Now it is asking what is the frequency and the period of given signals. So the signals are given and they are basically in the book, so you can check them. But here what I want to say to tell you is that if you have a signal like this, you have for example, this is like an exceptional signal. What is this period? Period is infinite because it goes like it has the like infinite wiggling somewhere far away, and now it has what it is the frequency. Frequency it is 1 divided by n, so it is 1 by infinity and it is 0, so it has 0 frequency. But also recall from aliasing that you can add, if you have also omega is 0, because 2 pi omega is 2 pi f, so 2 pi times 0, it will be, it results to omega that is 0. So omega 1 plus 2 pi, it can be 2 pi, and 2 pi refers to f that is 1. So basically this signal has the frequency of 0, and also the frequency of 1. Don't mind these smaller letters or capital letters, but you understand this because this is aliasing. So also this can have the frequency of 2. This is the case of aliasing, but if you know that it is 0, it's very good. Now other thing that I want to tell you, that is we are counting the spaces, yeah, to tell the period. So we have the period is the time from one maximum to one maximum, or from one minimum to one minimum, or from two equal points, yeah? So from maximum to maximum, okay? So from maximum to maximum, we have, this is 0, this is 1, this is 2. So we have two spaces, yeah? So n is 2, we have one cycle, so f is 1 by n, 1 by 2, and it is a half, yeah? So other signals you can find in the book. Now number 15. What are the units of frequency? And angular frequency. So frequency f and angular frequency omega. In continuous time, what it is the frequency? It is cycles per second or it is hertz. It is usually, it can be written also as second and superscript -1. So one cycle, we can write here cycle, one cycle per second is called 1 hertz. This is in continuous time. So here omega is radians per second, angular frequency. Discrete time, we have cycles per sample. And omega, here we have radians per sample. So this is what you need to know about the frequencies. And there you are, so write here as, okay, let's write here as cycles. I say one and write the other. So cycles per sample, cycles per second, radians per sample, okay. It's good. Now number 16. Determine the period and the frequency of a signal that will be given, okay? So imagine that you are getting a signal like this. So then it goes like this. Then it goes like this. It goes like this, then like this, and like this. Yeah, this is kind of signal. So okay, so here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I said that we are counting the gaps, yes? So beginning from this one, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So because we see that the signal is repeating here. and it has here again 1, 2, 3, 4, 5, 6 gaps. So this n is 6. 3, 4, 5, 6. Yeah, although signal finishes at 5. F is 1 divided by 6. Now what is the next question? 17. Signal xn cos pi n divided by 6. What is the unique signal? What is the unique signal? This is the allies signal, this one. What is the unique? Unique signal is, this is omega. So this is omega k. That's right. So 13 divided by 6 pi minus 2 pi, we get pi divided by 6. And we know that this is now omega 0 because we subtracted, yeah. Omega 1 was 13 pi divided by 6. And we see that this pi divided by 6 is in the interval from minus pi to pi. It's in this interval. So it is now the frequency of unique signal. So the signal is what? Xn cos pi divided by 6n. This is the answer. So now 18, number 18. So you need to differentiate between discrete time and continuous time signals in figures. So it's very easy. So it's CT and DT. How does CT look? CT looks, it is continuous signal. DT looks how? It is discrete time signal. Very easy. Yeah? Very easy to do this. 19. Maximal signal frequency in continuous time. Max frequency in CT. So what it is? F max is infinity. We have talked already about it. The stages of conversion of continuous time signal to discrete time signal. So the stages. So it is the stages. The first stage is what? It is discretization or sampling. We refer to time axis. Second stage is quantization. Refer to y-axis. The third is coding. So okay, so we finished with all the questions. Similar questions you will get in the midterm, and additional information I will write you in Moodle. So thank you, good luck.